I must admit that I had no intention of stopping the last lecture, because I was almost at the end. Now the problem is that I have no idea why my lectures are getting stopped precisely at 20 minutes. It just stops. I'm not handling anything, not doing anything, it just stops. I don't know whether it's of the memory or something, I have no clue. I'm just talking from my MacBook, opening the Photoshop. I have no clue exactly why it is stopping. So I was speaking about the bias and that just thing ended. It looks very bad, but it's tough on me to again go and redo and do everything in very little time. But this cannot be done, it needs time. So maybe I should learn how to break the things into smaller, not doing more than 17-18 minutes at a time, because I have no idea why it just stops. Because I had done things which had continued up to 30 minutes, 40, 30, 33 minutes, but for some reason it seems to stop. I just have no idea why. Okay, now let us look at the Cramer-Rao inequality. Let's go back. So this video is formally for the Cramer-Rao inequality. So you have estimated theta hat of the parameter theta, and the bias, which is a theta dependent value, is nothing but the expected value of theta hat minus theta. Then the variance of theta hat, that is what you want to know. How much the variance moves away from the expected value of theta hat. That expected value at theta hat could be actually theta. So how much the theta hat, if it is unbiased, then you are trying to know how much it moves away from the actual value of theta. When you take a statistic and you observe it, and when you compute the theta hat, the variance will tell you how much you have moved away from the actual value of theta, how much is your error. So variance is a measure of error, and that's very important. So you want to know what is the minimum error. So here what Cramer-Rao inequality says, that a variance of theta, it doesn't matter what is your state of things, cannot be less than this quantity. It will be always bigger than or equal to this quantity. Okay. And what is important is we are assuming that this bias is differentiable. But let us forget the bias business. This is not helpful when you have bias, just I told you in the last one. What is helpful here is to know that I can actually take an unbiased estimator. And once I have the unbiased estimator, then this is exactly what I have. When theta is unbiased, then variance of theta hat is 1 by the Fisher information of theta. The Fisher information associated with theta can be calculated from the sample. I don't have to bother about anything else. So that is what it is. And we call unbiased estimator an efficient estimator, a minimum variance estimator, if this is what happens. Because it gives me the minimum variance. The estimator which will give me the minimum variance, minimum move away from the actual value of theta, is the estimator we really want. So that's what it is. So an efficient estimator is one where the equality holds in the above inequality. Okay. Now let us look at normal distribution. So let us sample from normal distribution. We know that the mean is an unbiased estimator. Sample variance is also an unbiased estimator. We will not discuss it here. But your sample variance has always a lot of complications because of this n-1 term. Mean is an estimator, an unbiased estimator. So if I want to calculate the in theta, we would be able to know that is it really an efficient estimator. And we'll just show, the calculations are in the notes, that the mean is indeed an efficient estimator. So what's important is that you take the mean, compute the in theta, and invert the in theta and see if it is same as the variance of the mean. So given a random sample of size n, the variance of the mean for norm is always given by sigma square by n. Let us assume in this case sigma square is known to you. I'm just bothered about unknown mean. Then in the case of normal distribution, the Fisher score is given by x minus mu divided by sigma square. So if you take in theta, it is nothing but n copies of n times expectation of f xi theta whole square, which is nothing but the variance of f xi theta. Theta is basically mu in this case, so I'm just writing theta to make you sure that okay, I should write mu here, but okay, that doesn't matter. Now this is nothing but n by sigma 4. So this sigma square becomes sigma 4 when you take the square and bring out of the expectation. So it will be n by sigma 4 variance of xi. So that will be nothing but expectation of xi minus mu whole square. Just look at this expression and try to do the calculation, which is in the notes if you want to see it. So you will get finally n by sigma square, because this here I'll write sigma square. But what is variance of x bar or x n bar n, because n to show the sample size, is sigma square by n, which is same as I in theta. So x bar is an efficient estimator. So our study of parametric estimation ends here. We will not get into other details. I think that's not really required for the level, which is a 2-level thing. I don't think I would be. You might ask me about the proof of the Cramer-Rao inequality. The proof is there in the notes, but I don't know whether you should actually do the proof. I do not know whether a proof is really required for you, because that's, I think, asking too much. It would be more better in a graduate class. So I hope you have enjoyed these lectures. If there are any comments, please put in. Anybody can actually see the lectures. These are public on YouTube. I am not really finding any other way to communicate with you. So please forgive me for using this method. There is no other way to communicate. Hope that many of you are actually listening to these lectures. Again, I'll send a mail. I'll upload them very soon, and I'll send a mail to all of you. So thank you very much, and do stay safe, stay well, hoping that we again meet each other in our lovely campus. Thank you.